Hello everyone and welcome to today's online class for class 11. Do the comparison between the N2 plus, N2 minus and N2 minus species. All these species contain 1s, 2s, 2p orbitals, atomic orbitals. When they are constructing their molecular orbitals, 1s, 2s and 2p degenerate 3 orbitals combine all of them together to create the molecular orbital. Let's first construct the energy level diagram for these molecular orbitals. In the first species, 1s is there for atomic orbital 1. A little bit higher 2s is there, a little bit higher 3 degenerate 2p orbital is there. In a similar manner, on the second atomic orbital diagram, 1s is there, a little bit higher 2s is there, a little bit higher 3 degenerated 2p orbitals are there. In a similar manner, at first 2s orbital will combine and create the molecular orbital, antibonding and bonding molecular orbitals. Sigma 1 is, sigma star 1 is. In similar way, when 2s will combine, create 2 anti-atomic molecular orbital, 1 antibonding molecular orbital, 1 bonding molecular orbital. Sigma 2s, sigma star 2s. In similar way, one 2pz will combine with another 2pz and create sigma antibonding and sigma bonding 2p orbital. This is 2p sigma 2pz and this is sigma star 2pz. The remaining 2px and y, 2py will combine and create the pi molecular orbitals. This is the pi star 2px, 2py. This is pi 2px, 2py. This is the molecular orbital of the species that we are comparing. At first, let's compare N2 molecule. In nitrogen atom, there are 2 electrons in the 1s orbital, 2 electrons in the 2p orbital, and 3 electrons in the 2 electrons in the 2s orbital, 3 electrons in the 2p orbital. Similar will be for the second atom also. So the total numbers of electrons is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 numbers of electrons will be occupying this atomic molecular orbital in this manner. Pi will be singly filled first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then pairing will happen 11, 12, 13, 14. So this is the electronic this is how the molecular orbital will be filled for nitrogen, and the electronic configuration for nitrogen will be sigma 1 is to sigma star sigma 1 is to sigma star 1 is to sigma 2 is to sigma star 2 is to pi 2px, 2py 4 sigma 2pz 2. The bond order for N2 is going to be number of bonding electron 2, 4, 8, 10 minus of antibonding orbital electrons 2 and 2, 4 divided by 2, 3. This implies that nitrogen, the bond order of nitrogen is 3 and nitrogen molecule is constructed by 3 bond. Nitrogen is constructed by triple bond, which is actually true. Let's try to construct the energy level diagram for N2 plus species. For N2 plus species, one of the species, let's say this atom, this atomic orbital will contain 1 electron less, and thus will total number of electron that will be combined will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 electron will combine, and that they will be combined 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1 electron will be less in the 2p sigma 2p z electron, and thus the electronic configuration will be 1 is 2, sigma 1, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, pi 2px comma 2py 4, sigma 2pz1. This is the electronic configuration, and the bond order for N2 plus species is 1, 2 and 2, 4 and 4, 8 and 1, 9, minus of and number of antibonding electron 2 and 2, 4 by 2. This will give 2.5. 2.5. Let's construct N2 minus. For N2 minus species, the number of electron, let's say, will be 1 extra for the second atomic species, and that will give 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 electrons will be occupying this atomic orbital, and that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And now last electron will be occupying the pi star orbital, antibonding orbital, and the electronic configuration will be N2 minus sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, pi 2px 2py 4, sigma 2pz2, pi star 2px 2py 1. This is the electronic configuration for N2 minus, and the bond order for N2 minus 2, 2, 4, 4 and 4, 8, 8 and 2, 10, minus of number of antibonding electron 2 and 2, 4, 4 and 1, 5. This will give 2.5 bond order. Let's construct for N2 2 minus species. For N2 2 minus, let's say there will be another 1 extra electron in the second atomic species. This will be the total number of electrons as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 electron in total. 16 electron will be occupying this atomic orbital, and this will give 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Another electron will be occupying singly the pi star orbital, and the electronic configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px, 2py, 4, sigma 2pz2, pi star 2px, 2py2, and the bond order for N2 2 minus is going to be 2, 2, 4, 4 and 4, 8 and 2, 10, minus of 2 and 2, 4, 4 and 2, 6, 2. The bond order is 2. Hence, we can actually construct a stability order for the above species. The most stable will be N2, having the bond order 3, and then it will be N2 plus and N2 minus, because both of them have 2.5 bond order. But the number of electron in the bonding orbital is we need to calculate. In N2 plus, the number of electron in bonding is 9, and in antibonding is 4, whereas in N2 orbital, N2 minus orbital, the number of electron in bonding is 10, but in antibonding there are 5 electrons. As there are 5 electrons in bonding orbital and 4 electrons in antibonding orbital in N2 plus is comparatively more stable. Then N minus, and the least stable is N2 2 minus, because the bond order is 2. That's how the stability order can be constructed. The bond length also can be constructed on the basis of this bond order. It will be the reverse order of this stability order. Now we are going to compare the energy level diagram of O2, O2 plus, O2 minus and O2 2 minus species. Let's try to construct the energy level diagram first. Similarly, all of these atomic diagram will contain 1s, 2s and 3 degenerate 2p orbital also. The first atomic orbital diagram will contain 1s, a little bit higher, 2s, a little bit higher, 3 degenerate 2p orbitals. In the similar way, the second atomic orbital will contain also 1s, a little bit higher, 2s, a little bit higher, 3 degenerate 2p will be there. At first, when 2 1s will combine, they will create 2 atomic orbital, 2 molecular orbital, 1 bonding and 1 anti-bonding molecular orbital. Sigma 1s, sigma star 1 is. In similar way, when 2s orbital, atomic orbital will combine, they will create 2 molecular orbital, 1 anti-bonding, 1 bonding molecular orbital. Sigma 2s, sigma star 2s. 2pz will combine with another 2pz to create 1 bonding molecular orbital and 1 anti-bonding molecular orbital. And the remaining 2p x and y will create the pi bond. pi 2px 2py. This was the similar molecular diagram that I have constructed as that of the previous molecular diagram for nitrogen species. If you notice that pi 2px 2py degenerate orbitals are lower in energy compared to the sigma 2pz orbital. This should not be the case because these sigma orbitals are created due to the head-on collision, and head-on collision is more feasible collision, more penetrable collision, which should be create more stability. So this sigma 2pz should be lower in energy compared to this pi 2pz. But in the last examples that we had taken, this sigma star 2s has created a repulsion effect on this sigma 2pz. Due to that effect, sigma 2pz had increased in energy over this pi 2pz, 2px, 2py orbital. That's why we had constructed that MO diagram in this manner in our last example. But in this example, we had taken oxygen species. In oxygen species and onward the oxygen, that is species containing more than 16 electrons, those kind of species, in those kind of species, the repulsion effect coming from this 2p sigma star 2s has been minimized in a considerable amount. As a result, these 2pz and pi orbitals has interchanged their position like in this manner. That is, from oxygen species and onward, that is molecular species having more than 16 electron, the sigma 2pz will be lower in energy compared to the pi 2px and 2py. This is a very vital point we need to remember during the construction of energy level diagram of MOs. When we are constructing a molecular energy level having electron less than 16, in that case we will be drawing the diagram in which the pi molecular bonding orbital should be lowered compared to the sigma 2pz. But if we are constructing an MO for species which having 16 electron or more than 16 electron, in that case we will be drawing an MO in which this pi bonding orbital should be higher compared to the sigma 2pz orbital, like in this manner. Now let's construct the electrons, put the electrons in the respective values. Let's first construct the oxygen species. In oxygen atom, 2 electron occupy 1s, 2 electron occupy 2s orbital, and 4 electron occupies 2p orbital. The similar is the case for the another atomic species also. So total 16 electrons is there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 electron will be occupying this MO. It will start from the lowest energy MO, sigma 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is how this energy level diagram will be filled. And electronic configuration will be 1:2, sigma star 1:2, sigma 2:2, sigma star 2:2, pi 2px 2py 4 sigma, sorry, my fault, sigma 2pz 2 pi 2px 2py 4 pi star 2px 2py 2. This is how the electronic configuration for O2 species will be. Let's calculate the bond order for O2. This will be 1, 2 and 2, 4, 4 and 2, 6 and 4, 10, minus of 2 and 2, 4, 4 and 2, 6, 2. That is, the bond order of O2 molecule is 2. That implies that oxygen molecule has been constructed by double bond, which is true. Let's construct for O2 plus species. For O2 plus species, from the second atomic species, I am going to remove one electron by creating one electron less in this species and creating a class positive charge. If one electron is less in this species, that is that 15 electron has been constructed, and it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. One electron will be less, and the electronic configuration will be sigma 1 is 2, sigma 1 is star 2, sigma 2 is 2, sigma 2 is star 2, sigma 2 is 2, pi 2pz2, pi 2px 2py 4, pi star 2px 2py 1. This is the electronic configuration for O2 species, and the bond order for O2 plus is going to be 2 to 4, 4 and 2, 6, 6 and 14, 2 and 2, 4 and 1, 5, 2.5. Let's construct the bond order for O2 minus. For O2 minus, there will be an extra electron on the second species, making the entire atomic species negative in charge. Therefore, there will be another electron on the pi star, creating an atomic orbital, electronic configuration for atomic orbital as sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, sigma 2pz2, pi 2px 2py 4, pi star 2px 2py 3. The bond order for O2 minus species, 2 and 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Number of antibonding orbital 1, 2, 3, 4, 5, 6, 7. That is 1.5. Let's construct the bond order for O2 2 minus. The bond order for O2 2 minus is another electron will be there in the second atomic species, creating total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electron. That will give another electron on this. And atomic electronic configuration will be sigma 1 is 2, sigma star 1 is 2, sigma 2s2 sigma star 2s2 pi 2px 2py, sorry, pi will not going to be first, sigma 2py sigma 2pz2 pi 2px 2py 4 pi star 2px 2py equals to 4. So the bond order for O2 minus species is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electron minus antibonding orbital 1, 2, 3, 4, 5, 6, 7, 8. 8 by 2, 1. So the bond order is 1 for O2 2 minus. So hence if I have to construct the stability order, the most stable will be 2.5, that is O2 plus, then the stable will be O2, then the stable will be O2 minus, and the last least stable will be O2 2 minus. This is how with the help of MO, the stability order among these oxygen species can be explained.